Welcome back to this continuing series of lectures in the topics of the principles of macroeconomics. We're on topic 13 today, and last lecture we covered in great detail and length information about the Consumer Price Index. And in 13, as you can see, we have some index numbers from selected years from the most recent, in August of 2020, back to 1914, over 100 years ago. So we're going to use those numbers to do the calculations. Well, I'm not going to do the calculations. I think I may assign this topic, at least these calculations, as a homework assignment. So let's do some similar calculations. Let's do a calculation seeing what would be a good year. How about 1950? So the first one is, what was $1 in 2020 worth in 1914 dollars? And let's do 1950 here, but let's do it reverse. What is $1 today worth in terms of $1 in 1950? Okay, and before we do that calculation, let's review some formulas that we're going to need to do these calculations. And I have that here in this PowerPoint for topic 13. As you see, it's a pretty short PowerPoint, only 6 slides, including the title page. And here is the formula for calculating the inflation rate, which if we go back to this, we'll be using in D, E, and F. So I put that first because that's the first one given in the chapter. And I've modified a little bit in the second slide, and maybe I can write some notes here because typing it seems not so clear as writing it. So I'm going to, if I go to draw, I'm going to take this red. I'm not going to spell out later year and earlier year. I'm just going to use the letters to initialize it. So the formula for the inflation rate and I think I'll get out of red and go to, I like blue. So the formula is going to be the CPI in the later year or the later time period minus the CPI in the earlier one, and that's supposed to be an L, doesn't exactly look like it, and that's divided by the CPI in the earlier year. So basically the change in the index number over the original index number, that gives you a ratio, basically a percent, if you multiply it times 100, okay? And so that's, I just understand it better written like that than typed out. But then up here, I have manipulated this a little bit so I can change this up to, in the parentheses, CPI in the later year divided by the, and that should be an I, not an L. I was getting ahead of myself. The CPI in the earlier year minus the CPI in the earlier year divided by the CPI in the earlier year. So this is a common denominator now, times 100. And we can rewrite this really as the CPI in the later year divided by the CPI in the earlier year minus 1 times 100. All right. So some students find that they prefer this formula for the inflation rate. And basically, if we subtract 100 from the index number, we can get the percent change in prices over the time period under investigation, and we might do that in a moment. So let's see what we have next. I want to see what I've done. Remind myself. Okay. So they also want to deflate things and state them in real terms. And basically you do that by taking the nominal price or nominal income divided by the CPI at the time the nominal income is observed, multiply it times 100, and you get the real income. And really what they're not saying, in base year prices. Oh, I wrote that out because the slide from the textbook didn't. And the reason I know that is that this can be changed into a ratio similar to the formula I'm going to introduce, which the textbook doesn't, comparing the price of something across time or deflating the price of something in one year to the prices of another. And the word deflating, confusingly, is even used when you are increasing the price of an earlier year to the prices in the current year, given that we have been experiencing inflation pretty constantly for a very long time. So we can rewrite the real income formula into one that is easier to remember and which can be generalized into a formula that can deflate nominal income in any year into real income of some other year. In the formula of the previous slide, the CPI 100 equals the CPI of the base year. And that's by definition when we are talking about the CPI. So let's replace the CPI 100 with this term, CPI in year one. Let's also replace that nominal income with income in year two, and CPI with, that we divide into the nominal income with CPI in year two. So then we get something like this. Real income equals divided by CPI in year one equals nominal income in the year in which the nominal income is observed. So now we solve for we can solve for real income in terms of any year you're interested in, not only the base year, say July of 1983. So generalizing this formula even more so, we can actually put it like this. The price, or nominal income, if nominal is here, or the price in any year divided by the CPI in the year. If you want to know the prices, what that would be equal to in the prices of some other year, you can use this formula. Price in year two equals the CPI in year 2. So basically, I know this seems confusing, but given the price in year 2, right here, and the CPI numbers, both of which you know, you can solve for the equivalent price in year 1, and vice versa. Given the price in year 1 and the CPI numbers, which will always be given, you can solve for the equivalent price in year 2. We can use this information to determine if the real price of the good has increased, decreased, or remained unchanged. Okay. So let's start off using this formula. Let me go back to the questions. And I say, what is a dollar worth? And I think we'll say, what was a dollar today? And this would be August of 2020, worth in 1950 prices, okay? And so we have the CPI. We have the CPI of the most recent, 259.9, and in 1950 it was 25. Let's return to the PowerPoint, and let's go home. Let's add a new slide. I hope I can write in the blank. Let me see if I can. Oh yeah, I can, I think. Cool. Draw. So, we have the worth of the dollar in 1950. So let's just put price of 1950 over CPI in 1950 should equal the worth of a dollar today over the CPI, well, not today, but last month in 8/2020, okay? And plugging in what we know this value, we know this value, and this value is given. So we solve for this. So we have the price of a dollar, how much a dollar is equivalent to a 1950, over the CPI in 50, 25, over $1 in 2020, and 259.9. And then we solve for this. And so the price or value of the dollar, if that is easier on your ears, equals $25 divided by 259.9. And let's bring my calculator up. And that would be 25 divided by 259.9. And it looks like it's going to be worth 9 cents. We can round. It would be 9.6 cents. Let's just use that. What the heck? So this equals 9.6 cents. So basically what this is telling us is that a dollar today buys basically what a dime bought in 1950, 70 years ago. So there's been a huge devaluation of the dollar over the last 70 years. It's lost its purchasing power by a substantial amount. And you can almost do the inverse of this if you said 10 cents. 10 cents is 1/10 of a dollar. So basically, a dollar today, let me put it another way. $10 today buys the same as $1 bought in 1950. All right? So hopefully that gives you some insight into how to solve, say, A and B. Let's do one on B too. Now, I think this one may interest you. I hope it does. I know more people were interested in going to A&M than UT, but I know I found out the tuition and fees cost at UT in the mid-60s, basically at the time of the passage of Medicare and Medicaid. And Medicare and Medicaid have a lot to do with rising tuition. But we might talk about that at some other time. Let's go to another slide if I can. And so let's see what the tuition for one semester in the mid-1960s was about, and that's tuition and fees, $100. All right. The question is, adjusting for inflation, how much is that equal to in the latest, let's just say 7 or 8 2020 dollars, okay? And so basically we have that same ratio, which is tuition mid-60s over CPI. I hope I have mid-60s. I think I do. In mid-60s. I think I have 66 there, actually. But we could go look it up for 65. Equals basically value today for CPI 8/2020, okay? You know, I think I still have it up. Oh yeah, here it is. All of the numbers from the beginning to the end. Let's just look for 65. What should we use? Let's use August 65. How about that? When you're going to have to pay tuition. So that would be 31.6. All right, 31.6. So we're given the tuition in the mid-60s as 100. 31.6 equals the value today. I'm just going to put X. I don't want to write it out. All over 259.9. And so we're to solve for X. So X is going to equal $100 times 259.9, all divided by 31.6. Let's get the calculator up and give it a spin. Well, 100 times 259.9 divided by 31.6 is $822. Whoops, maybe a little bit more. Yeah, probably. And 46 cents. So, if there had been no inflation and the tuition had remained constant, in real terms, the tuition at UT would be $822.46 a semester. I'm sure your parents, and even you, if you're paying for it, would be happy to pay that amount versus what it costs today. But let's see what the cost today is. And I'm not sure, but last spring, my students who were enrolled at UT were saying that tuition in spring of 2020 per semester was about $6,500. So there's been the cost, the real cost, the opportunity cost, the purchasing power cost of tuition has gone up by an extraordinary amount. Let's just see how much it went up. And I think here you can just do a simple division. What was it? 822. So the tuition now, let's say, is 6,500, and the equivalent, adjusted for inflation, was 822.46. Yeah, we're being sort of ridiculous and being so precise. So this ratio is actually, if we bring up the calculator again, how many times is that? That's 6,500 divided by 822.46. 7.9, so 7.9, almost 8 times. 7.9 times as expensive. What is that in percentage terms? I think it's 790%, but could be more. We may need to add 100, because double 100% more would be 1,600. That's twice. Twice is 100%. No. So this is 8 would be 700%. So this is actually more close approximately to 700% increase in the real cost of tuition at UT Austin. All right. Okay, so that's another problem we've solved. Let's go back here. So hopefully, you see how to do A, B, C. Let's do some of these inflation ones. What can we do? Let's, instead of using this table, let's use the table I brought up over here. Let's go to a year that I know had pretty high inflation. Let's look. This is December And so what do we have? 78. Oh yeah, look at this jump. Let's do from December of 79 to December of 80. So December of 79, 1279, the CPI was 76.7. And a year later, it was 86.3. So let's see what the annual inflation rate was over that year, basically over the year 1980. And here we'll come back to my PowerPoint and we'll draw a red line here separating the two. So the inflation rate, and let me draw it in black now, is, and this is over a 1-year period, that's supposed to be CPI in later year, 80, minus CPI in earlier year, that's 79, all divided by CPI in earlier year, 79 times 100. So let's put these numbers in. 86.3 minus 76.7 divided by 76.7, and then that's times 100, okay? And so we're going to get, wow, that's 10. So if this were 86.7, it would be 10, but it's a little less. So it's 9.4, right? There's 9.4 all over 76.7. Ooh, it's going to be a big number. Boy, people would be unhappy if that were the inflation rate. Now, let's pray that we don't ever experience that again or even higher. So let's go 9.4 divided by 76.7. Find out what that number is, and then multiply by 100. And so the inflation rate was it 12.25, I believe, percent in 1 year. Wow. Wow, wow. They call it the rule of 72, or sometimes I've heard it as a rule of 69. Basically, if you take a rate into 72 or 69, you get how long it would take to double, or in the other direction, have a value. So if we divide it 12.5, let's just do it, let's use 72. 72 divided by 0.25. So in a little less than 6 years, the value of the dollar would fall by half. Huh. Interesting. Maybe we can do one more. Let's look at this thing again. And we have from July to August. Let's find out what the inflation rate was from July to August of this year. So let me write this down so I don't have to come back to it. In 720, it was 259.101. And in 820, it was 259.101. 918, 101 and 9.8. All right, so now we do this calculation, and I guess we can go to these additional slides don't cost anything. So we're back here, and we're doing the inflation rate again. So what we're looking at, let's do it in a different way, like the second formula for this. So we do it in the CPI in that would be 820 divided by the CPI in the earlier period, 720 minus 1 times 100. This is just a month, so it'll be pretty small it's been almost none in that period of time. So really we have 259.918 divided by 259.1. I can't see what I wrote down. I think 101 minus 1 times 100. All right. So let's do these calculations. 259. Whoops! I need to bring my calculator up. 259. .918 divided by 259.101 equals, let's shrink that down. I can't move it, huh? I want to move it out of the way. There we go. 315. So this is basically equal 1.00315 minus 1 times 100. Let's bring our calculator back up, and let's multiply that by 100. Oh, I forgot. No. Let's divide by 100, and we'll get back to our old answer. And let's subtract 1 from it. There we go. And now multiply that by 100, and you get the answer as being 0.32% inflation over a month. And I suppose that's a per monthly period of time. So a rate is always time. Now let's multiply that times 12 to see if we can get an approximation on what the yearly inflation rate would be. So times 12. Oh, that's pretty high. So 3.8% on annual basis. Ooh, that's getting up there. I don't like that very much. Oh my goodness. All right. So there are some complications I can talk to you about, but it's not a math course. I'm not that worried about it. I do have an inflation rate from December 29 to March 33. And so that would be, what, 30, 31, 32. That's 36 months plus 4. That's 40 months. little over 3 years, but that's the rate over 40 months. If we wanted to get it down to a monthly basis or even an annual basis, we would have to, I think the easiest way to get it, to figure out what the average annual rate would be to do a compound interest type formula and work it backwards. The same goes for the inflation rate from 70 to 81. That's 11 years. So you're going to find the inflation rate over an 11-year period of time, how much prices had gone up in 11 years rate per period of time. If you wanted an annual one, you would have to do a sort of compound interest type of thing. And maybe I should explain myself on the compound interest. Oh, gosh, I don't know. Should I not? I guess so. Why not? I'm dealing with a group of very smart students. So basically, if you put like your principal into savings of $100 at 5% interest 1 year later, you would have, God, I wish I were earning that much, $105. So basically, the amount a year later is going to equal the principal times 1 plus the rate of interest, okay? And really, implicitly, there's a 1 up here in 1 year. So after 2 years, this is how much you have after 1 year. Now this is going to earn interest, 1 plus r, okay? So it's p times, 1 plus r squared. And then, of course, you can generalize. It's going to be p times 1 plus r to the nth, okay? Is how much it'll be worth after so many periods of time. Now, what we want to solve for, really over 11 years, would be r. And so I start unpacking this formula by dividing through by p. So a sub n is the number of periods, divided by the principal, or the amount we started with, would equal 1 plus r to the nth. I guess if this were squared, you'd see that I could take the square root of it and the square root of this, but I'm going to do something slightly different. So a to the nth over p to 1 over n is going to equal 1 plus r. So r, which is now the inflation rate, is going to equal the amount, or the index number we ended with, divided by the index number we started with, all taken to the nth root, minus 1. And that'll give us r, which would give us a very close approximation to the annual inflation rate over a period of time. I guess for the Great Depression, 40 months. Oh, gosh, can you do fractions? I don't see why not. Divided by 12, that's 3.25 years, right? And this is from, what is it? Was it 1129 to 333? And then from 1970 to 1981, that's n equals 11. And then you can figure out what the annual inflation rate is. But I'm not asking you to do that. I just was saying that, yeah, since it's a rate, usually it's in annually. Okay, I'm going to see if I can assign number 13 as a homework assignment. That does it for number 13. See you when I talk about number